In this video, we're given some information about the graph of a rational function, and we want to generate or come up with the function that satisfies this information. So we're given that it has vertical asymptotes at x equal -2, x equal to 2. Those are the equations of the asymptotes. As a horizontal asymptote, y equal 1, and the y, or the x and the y-intercept, have the point 0, 0. So all we're going to do here is actually go backwards. When you're going to graph a rational function, one of the first things you do is find the equations of the asymptotes, vertical and horizontal. Find any intercepts that it might have. You might consider the domain, and from that information you sketch the graph. So a rational function will have the form, I can call it f or y or g of x, whatever. I call it f of x. And you're going to have a numerator that'll be a function of x. You'll have a denominator that have a function of x. Now the numerator can be a constant, just a number. The denominator, you have to have an x, a variable. So you can have something as basic as 1 over x. That would be considered a rational function. Whereas x over 1 is just plain old x. So that's a first degree function, that's a line. So that wouldn't qualify. So let's start off with the asymptotes, the vertical ones. We know that the vertical asymptotes comes from numbers that make the denominator 0, but not the numerator. So x equal -2, x equal 2, they'll make the denominator 0. So that would suggest then that x plus 2 and x minus 2 have to be factors of the denominator. Put a -2 here for x, -2 and 2 is 0, 0 times anything is 0. Put a 2 here, 2 minus 2 is 0. 0 times anything is 0, so that satisfies that. So again, the asymptotes, vertical asymptotes, comes from a number that make the denominator 0, but not the numerator. So that condition is satisfied. Now let's go to the x and y-intercept. To find the y-intercept, you replace the x by 0. So do it this way, put a 0 where the x is, then the y has to come out to 0. Okay, so let's look at this. Okay, if I had a 2 in the numerator, replacing the x by 0, I would get 2 times -2 in the denominator, -4. But the numerator would say 2. That's not going to give me 0. So I have to have an x up there. Or an x squared, or an x cubed. That'll work. But we'll start off with a plain old x. Put an x there. I notice if I replace the x by 0, I get a 0 in the numerator, -4 in the denominator. That'll give me 0. That'll work. Now, to get the x-intercept, I replace the y by 0. Okay, so the y would be over here. That's your f of x. Put a 0 there, and then when is this right side 0? Well, it's going to be 0 when the numerator is 0. That, of course, is going to be 0. So that'll work. So what I have there will satisfy this condition and this condition. But now I have to satisfy the fact that it has a horizontal asymptote at y equal to 1. So what do we know about the horizontal asymptotes? We know that horizontal asymptotes will occur when the degree of the numerator is less than the degree of the denominator. Remember, this is, if I multiply this out, this is going to give me x squared minus 4. So the degree of the numerator here is 1. The degree of the denominator is 2. Now when the degree of the numerator is less than the degree of the denominator, y equals 0 will correspond to your horizontal asymptote. That, of course, is your x-axis. But we have to have y equal 1. So let me just, again, go over that. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will always be y equal to 0. We don't want y equal to 0, we want y equal to 1. The other situation you can have, if the degree of the numerator is the same as the degree of the denominator. Okay, so let's make this, let's increase it by 1. This is x squared. Now this is x squared, so it's 2 and 2. The degrees are the same. If the degree of the numerator is the same as the degree of the denominator, then you take the coefficient of the lead term on top over the coefficient of the lead term at the bottom, so it's 1 over 1, and that gives me this. Now, important to note here that if the degree of the numerator is larger than the degree of the denominator, you don't have a horizontal But you can have an oblique. If the degree is one more, if the degree of the numerator is one more than the degree of the denominator, then you have an oblique or slant asymptote. You would have to use division to get the equation. I've done some videos involving that, but for right now we just want the equation. So here it satisfies it. So this one right here is the function that satisfies those conditions. I want to put out that I want to say here that it's possible that in some situations you might have more than one answer. In this case, we just have this one here, and all you have to do is, again, test it out. You can see it satisfies all the conditions. Vertical asymptotes, -2 and 2, horizontal, y equal 1, and it does have x and y intercept at 0, 0. You can easily graph this. I'm going to clear this just to show you that this is it, but this is all you need here. But just to give you some more information, you can stop here if you want. I've got this right here. So the information we have, this is one vertical asymptote x equal -2, or 2 rather, and then x equal -2 over here. Then we have the horizontal y equal to 1. And I'd gone through some videos before I go through the procedure. We have a x and y intercept here. This graph is going to go down like this, kind of like a parabola. And over here we have the vertical and the horizontal, so we have to have a graph that approaches both. So this one kind of goes in like this. And over here the same thing. You can pick values in each of these regions to test out where the graph is, above or below. And I've done some videos like that. But just to give you the graph of that function that we generated, this is what you should have. Thanks for watching. We'll see you next time.